Hello everybody. In this video we're going to talk about something called conservation of momentum. So before I dive in, just a reminder that momentum in physics is denoted with the letter P, and it's the product of mass and velocity. Okay, P equals mv is the equation for momentum. So if you got an object that's moving, right, with some velocity, then it has momentum. If that object is staying at rest, then its velocity is 0, and therefore it has no momentum. It's as simple as that. And then this idea of momentum is now a new quantity in physics, similar to energy, that is actually conserved. And so we call it the law of conservation of momentum. And the law just states that the total amount of momentum before and after a collision or an explosion remains the same within a system of objects. Okay, so in this picture over here, I've got a collision between a van and a car. And so the total momentum of the two of them before the collision is going to be equal to the total momentum of the two of them after the collision. That's the idea of momentum being conserved. Looking over here, but how can momentum be conserved when a collision or an explosion causes the mass or the velocity of the objects to change? Well, the increase in momentum of one object will always equal the decrease in momentum of the other object, so that the total of all objects remains the same. Okay, and the law of conservation of momentum can be hugely helpful for solving problems involving collisions between objects or the explosion of a single object. Okay, and so we're going to look at 3 different types of interactions that involve momentum conservation. So in the first one, it's called an elastic collision. Okay, during elastic collisions, objects bounce off of each other. So when you think of elastic, think of bouncing. Objects bounce off each other, such as when 2 bumper cars or 2 billiard balls collide. The total momentum of both objects before the collision will be equal to the total momentum of both objects after the collision, like this. So we've got the mass and velocity of the first object before the collision. So let's kind of draw this out. So here's maybe the mass of the first object, and let's say it's moving this way with some initial velocity that I'll call V1 initial. And let's say there's a second object over here, which I'll call mass 2, and it's maybe moving the other direction. So the two objects are moving towards each other, and it's got V2 initial, the initial velocity of the second object. Okay, and then they're going to collide, and then they might come to a dead stop, or they might both move to the left, or they might both move to the right, depending on which one has more momentum. But the idea is that after the collision, we would expect new velocities. So here's M1, and maybe it's going to continue moving to the right now with V1 final, its final velocity, and then the second object, which I'll maybe call M2, is now going to move with V2 final, okay, its final velocity. So that's for an elastic collision when objects are bouncing off of each other. There are 2 individual objects before the collision, and there are 2 individual objects after the collision. Okay, what about an inelastic collision? Okay, so during an inelastic collision, objects actually stick to each other. Okay, and they become like one combined mass. And so now we have a new equation here, which says that the momentum of the first object, let me actually slow this down, the momentum of the first object plus the momentum of the second object before the collision will be equal to the combined momentum of both objects after the collision. Well, after the collision, they're going to stick together, right? So their masses are going to join up. But since they're one combined object, they will just move with a common velocity, which I'll call V12 final. So the picture would look like this. So you'd still have your first mass moving with an initial velocity, V1 initial, and you'd still have your second mass moving with an initial velocity, call that V2 initial. But then after they collide, they're going to stick together. So you're going to have this like combined thing, which I'll call M1 plus M2, right? They're like smashing together and combining, and they're going to move now just with a common velocity that I'll call V12 final. So examples of this, it says the objects stick to each other, and I'm finishing up this paragraph in here. Objects stick to each other or embed in one another, such as when football players tackle, when a bullet hits a wall, or when two balls of clay collide. Since the two objects become a single combined object after the collision, the conservation of momentum equation simplifies. And then we have this third option, which is really the exact opposite of an inelastic collision, called an explosion, okay? During an explosion, a single object separates into several unique objects due to the force of the explosion. So here's how an explosion would work. We would have originally this single object, and after the explosion, it separates. And this is going to have some velocity, v initial. And it, maybe it's going this way. And then after the explosion, they separate into two pieces, M1 and M2. So M1 moves this way, M2 moves this way. So M1 has its own final velocity, and M2 has its own final velocity. Okay? And so the way that that works out mathematically is that the momentum of the combined object before the collision is going to be equal to the momentum of the first object after the collision plus the momentum of the second object after the collision. And then in my next video, I'm going to go through examples, one example of a elastic collision, one example of an inelastic collision, one example of an explosion to show you how this really works out.